Hello, everyone. Good morning, good afternoon, good evening. Thank you so much for joining us for today's Science Talk. I'm thrilled to welcome you to UNU-INWEH's Science Talk. I'm Dr. Miriam Axel. I'm delighted to be your host. For those of you who are joining us for the first time, we'd like to remind you that all of our previous Science Talks from the entire 2024 series, as well as those from 2025, are available on our website at unu.edu/INWEH/science-talks with an S at the end. Today's talk, like all others, will be recorded, and the recording will be made available after the session. I'd also like to remind you that we will conclude with an interactive Q&A session at the end of the talk, so please use the Q&A box to put your questions in, and I will be sure to read them to our speaker. Topic of today's talk is uneven ground. Who bears the weight of a sinking coast? Remote sensing-based monitoring of land subsidence in densely populated coastal regions and critical economic hubs. And it's my great honor and pleasure to introduce today's speaker, Professor Manoochehr Shirzaei, who is now the chief scientist of the Global Lab for Environmental Intelligence, which he will discuss as well. Dr. Shirzaei's research is focused on spaceborne synthetic aperture radar technology, groundwater resources management, green energies, and equitable adaptation to natural and anthropogenic land subsidence, sea level change, and coastal hazards in the face of a changing climate. He's the lead for subsidence analytics at UNU-INWEH and is leading a new transdisciplinary research initiative, which is at the intersection of climate change, infrastructure resilience, environmental security, societal risk, and his work focuses on emerging issues that relate to detecting land subsidence, developing engineering and nature-based adaptation and mitigation strategies, and evaluating communities and infrastructure systems risk under extreme events and compounded hazards. Dr. Shirzaei is Associate Professor of Radar, Remote Sensing Engineering, and Environmental Security at the Department of Geosciences and National Security Institute of Virginia Tech. He's authored over 250 peer-reviewed articles, technical reports, and other publications, and has supervised over 60 postdocs, PhDs, masters, and undergraduate students. He's also received several awards from the U.S. Department of Energy, the U.S. Department of Defense, and the U.S. National Science Foundation and Virginia Tech. Professor Shirzaei has been a member of the NASA Sea Level Change Team and NASA GRACE Satellite Science Team, and he serves on the Southern California Earthquake Center Geodesy Committee and the U.S. Geological Survey's Coastal Flood Modeling Team. And he's also the U.S. representative at the UNESCO Land Subsidence International Initiative. And now, without further ado, it's my great pleasure to turn it over to you, Professor Shirzaei.
Oh, thank you very much for the introduction. It's such a great and pleasure and honor to speak to you all. And I would start my presentation by thanking many co-authors that participated and collaborated and actually produced quite a bit of this result, as well as funding agencies, some of them you mentioned, such as DoD, DOE, NSF, and NASA. So the title of the talk, as you can see, is Uneven Ground and Who Bears the Weight of the Sinking Land or Coast. So we want to discuss some of the work that we have done over the past few years in quantifying land subsidence and how that impacts communities and environments across the United States. And eventually we have outlooks how to implement that through this new initiative that we started at the United Nations University, how to expand this to the global and make this data available to everybody and help everybody to make better decisions in the face of climate change. So to begin with, what is land subsidence? So land subsidence is any process that lowers the land. We call it land subsidence, the impact of that. So if you look at the literature, one of the first examples of the land subsidence that made it to the courtroom and has significant precedent is the oil fields in South Texas called Goose Creek. This one was one of the largest oil field at this time, and due to extraction of the oil and gas from the underground, land elevation sank, and at some point in 1920, quite a bit of the oil fields was under the ground, under the water, as you can see it in this picture to the left. This created opportunity for the state of Texas to claim that this oil field belonged to the states because, according to state law, any land, any resources that is under the surface of the water is a state law and cannot be privatized. So oil field owners hire two geologists to argue in the courtroom that this is not act of the God, it's act of the human. And that's where the first principle of the pearlasticity that result into due to extraction of the fluid result into lowering pressure within reservoir and causes collapse of the reservoir and subsidence along the over the surface due to that was established. And surprisingly, the oil field won the case. So thanks to the scientists that argued that this is not act of God but act of human due to extraction of the fluids that caused land subsidence. So this is the oldest case that we know that was discussed from scientific perspective and had law and other implications. And later on, if you fast forward, we see land subsidence in many places. So this is another historical and very important case of the land subsidence that even goes on today. It's Central Valley in California, which produce almost a fifth of the food consumed in the United States. So as you can see in the middle, there is a famous picture of a pole. It's a power pole that shows elevation of the land where it was at different times. So in 1925, land elevation was here, and it lowered in the course of almost 50 years to here. And to the left is a picture of my friend Michelle Sneeds. She shows that in the course of 25 years, almost 5 feet land subsidence happened in different locations across the San Joaquin Valley in South Central Valley, California. Looking at the global scale, land subsidence is impacting almost 10% of the global land. And this is a conservative estimate. So we believe that this number is much higher. And the reason for the underestimation is just lack of data at the moment. What drives the land subsidence? So there are many processes, some of this natural, but some are anthropogenic, human-made, that drive the land subsidence. So looking at this hypothetical profile across the Northern America, going from the west, which is Cascadia, to the east, which is the East Coast, New York, we have different processes in play that have different spatial extent, but also different temporal variation. So tectonic processes are generally slow, causing the land elevation to rise or fall depending on where you are located with respect to the subduction zone. And during the earthquake, the sign of the motion flips. So where it was going up would subside, and where it was subsiding may rise. These processes impact hundreds to thousands of kilometers depending on size of the earthquakes and extent of the fault. When you go further inland, when you go further inland, the other process that drives the land elevation change, which is human-made, is extraction of the fluid, whether water or oil and gas. These processes usually are very localized, but change rapidly in time and can cause tens of centimeters subsidence in a short period of time. Entire Northern America is affected by a process called glacial isostatic adjustment, or GIA. So as a result of removal of the big glacier that covered northern part of the America and Canada almost 15,000 years ago, land is rising in Canada. And in perimeter of that, to have the mass conserved, land has to subside. So that's why part of United States and eastern coast of United States particularly are subsiding at a rate of 1 to 3 millimeters per year today. And then we have compaction of the sediments. Sediments are added to the coastal area through different processes, and they are usually very soft and loose. Under their own weight, they continue to subside and compact, and that drives also the land elevation loss or subsidence. In most places around the world, we have a combination of these two processes, these four processes. So very seldom we can have a place that only one process in place. So what you see here, each circle is one measurement station, and the color codes show the uplift or subsidence along the coast of United States. Where we have red, land is subsiding, and when we have blue and cyan, land is rising. As you can see, in the northern part of the Canada and the United States, Northern America and Greenland, land is rising, and that's because of that GI effect mostly. While in the East Coast and Gulf Coast of the United States, land is subsiding, and that's mostly due to compaction of the sediment, but also extraction of the oil and gas and water. And the same happens in the southern part of the Asia and Southeast Asia, that quite a bit of land subsidence happens due to a combination of processes of groundwater extraction and compaction of the sediment. And this land subsidence cause hazards. So the hazard associated with land subsidence could be damage to infrastructures and buildings, but also exacerbating effect of flooding. So how land subsidence can damage building? If you have uniform or even land subsidence, infrastructures such as building can withstand that without undergoing any kind of damage. But if you have differential land subsidence, as you see here, one side of the building, one leg of the building is going down faster than the other side. As a result of that, building experience a tilt. That we call angular distortion. And that angular distortion is suggested to be a cause that exacerbates or increase the likelihood of a building collapse when other factors play together. So for example, many buildings in Florida are subsiding. Important case of that is Surfside condo that collapsed a couple of years ago. And this building was shown that has been subsiding years prior to the collapse. And I want to emphasize that this building that collapsed had other issues such as poor construction material and poor design. So land subsidence often has a compounding effect, combines with the other factors and promotes and exacerbates the likelihood of building collapse in different places that it happened. At the same time, land subsidence can increase flooding risk by compounding effect of the sea level rise. Sea levels are rising around the world at the average rate of 4 millimeters per year, roughly. And this rate is varying from location to location due to local processes. And land subsidence, which is often a local process, can exacerbate the rate of sea level rise, which we call the combination of two together, relative sea level rise. And relative sea level rise is the factor that determines the flooding risk at the coastal areas. So this is a case example that I would like you to highlight here. Jakarta in Indonesia is a city that has been sinking at the rate of tens of centimeters per year due to mostly groundwater extraction, but also some tectonic processes. And sea level has been rising also rapidly. So the situation is so bad that every year they have to increase the height of the flood protection infrastructures, and that's not enough. And city often get flooded. So the situation is bad to the extent that government has decided to move the capital city of Jakarta to different city with the hope to mobilize some of the population and also protect some of the key infrastructures at different places. So land subsidence, as I mentioned, has been happening in different places, but the data for it is scarce. So we don't have many measurements still today to quantify land subsidence at global scale. Some of the measurement tools for quantifying rate of land subsidence are shown here. So the advantage of these tools, whether GNSS, extensometer, tiltmeter, leveling, is that they provide us with the very precise measurement, but point-wise observation, which means they are great in quality and sometimes in sampling rate in time, but they don't have adequate coverage in space. To overcome this limitation and provide observation that are of high quality and great sampling rate in time, and also high spatial resolution, we use satellite radar interferometry. This is active imaging technique, transmit radar signal that penetrate through the cloud, hit the ground, bounces back to the satellite. By collecting these return measurements, we can tell something about what happens at or near the surface, such as biomass distribution that has been mapped for first time using radar technology, but also geohazards such as volcanic deformation, as well as tracking, for example, iceberg to improve safety of the maritime and many other applications. So we have access to many radar satellites free of charge since 1992, starting with the ERS-1 and 2 satellites launched by European Space Agency. And today we have access to many satellites that are categorized here based on wavelengths, X, C, and L band. And among those, I want to highlight the Sentinel-1 satellite, which is a European Space Agency satellite operated since 2015 and has been providing us with the data at very high quality and precision, free of charge, anywhere around the planet. And hopefully within the next couple of days, the InSAR satellite, which is a joint venture between NASA and ISRO, Indian Space Agency, and this satellite will also provide us with valuable information that can be used to monitor the Earth's surface and capture dynamics of the Earth's surface as it happens on the go. And private sectors has been extremely active too. So for example, ISI is a private company that operates a fleet of small satellites, can provide satellite data, radar satellite data, free of charge, at the charge, but sometimes receives them at the reduced cost for research and civil applications. And this data can be used to detect many different changes and hazards around the world with the sampling rate of almost 1 image a day, or even better. So how InSAR works? In the next few slides, through a cartoon, I visualize how interferometric synthetic aperture radar for measuring land elevation change is working. So this is Hawaii Islands, house to 2 active volcanoes, Kilauea and Mauna Loa. Assumes that the satellite flies over the Hawaii Island, transmits radar signal, collect a backscatter, and create that image. So now satellite goes around and comes back sometimes later, transmit the same radar signal, collect a backscatter, and create second image. Combination of these 2 images together allows us to create an interferogram. So this interferogram contains mostly phase changes in the line of sight of the satellite due to change in elevation and change in the topography from the satellite perspective. By taking a reference digital elevation model, SRTM, and subtracting that from that interferogram, we are able to create a differential interferogram. What you see here is mostly change in elevation toward or away from the satellite. So for example, you see this contour line here, we call them fringe, represents change in elevation due to volcanic inflation and deflation in the line of the sight of the satellite. So now satellite flies over the area many times. By collecting repeated measurements, we can animate the surface deformation and create a time series of the surface deformation that has significant implication to understand dynamics of the process that shapes the landscape. So there are many different tools and frameworks to do this InSAR time series analysis. A framework has been developed in my lab. It's one of the world's most advanced algorithms called wavelet-based multi-temporal InSAR or WebInSAR that leverages a significant amount of AI and signal processing tools and techniques to reduce atmospheric and other environmental artifacts and create maps of surface deformation at the precision of better than 1 millimeter per year. So there is lots of publication, and a version of the software is available on our website for public use free of charge. And I would be happy to answer any further question if you have at the end on this software and application of it. So lands are sinking. Land along the coast, particularly coast of United States that we studied here, are sinking. So almost 80% of the coastal areas are going down at a rate faster than 0.1 millimeter per year. And almost 20% of the coastal land around the coast of United States are sinking at the rate faster than 4 millimeters per year. The 4 millimeter per year is critical because that's the average rate of the sea level rise. So 20% of the land along the coast of the United States going down faster than sea level is rising. So it means that in those areas, coastal hazard is mainly driven by land subsidence rather than by sea level rise. So these are profiled along the three coasts, East Coast, Gulf Coast, and West Coast, and shows the elevation change or land subsidence along the coast for each coast separately. And some of the key cities are highlighted. So on the East Coast, Chesapeake Bay has the rate of almost 8 millimeter per year subsidence, which is over here. And cities like Charleston and Savannah follow that with the highest rate of land subsidence. That is mostly driven by compaction of the sediment, but also GIA. In the Gulf Coast area, we have city of Biloxi and also Mississippi Delta that experience fastest rate of land subsidence up to 1 centimeter per year. And on the West Coast, we have cities like Monterey and San Francisco Bay, as well as the San Diego that are experiencing subsidence varying between 1 or 2 millimeter to 5 or 6 millimeter per year. And these are a significant rate of land subsidence for the coastal area because they are mostly flat, and also they are exposed to rising sea level. So continuing that study, this is a paper that's going to be published very soon. Tomorrow morning, it will come out in Nature City. We examined the inland cities as well. So we thought that when subsidence happen along the coast, why it should not happen inland? And we monitored 28 cities across the United States, and we detect a various rate of land subsidence in most of these cities. And that some reaches up to 6 millimeter per year. To our surprise, the fastest rate of land subsidence is observed in Texas. Cities like Houston and San Antonio experience rates as fast as 6 millimeter per year. So looking into the spatial distribution of the land subsidence for some of the city, the middle one is Texas. As you can see, land subsidence is fastest in the perimeter of the city and slows down toward the center of the city. That's mainly driven by the compaction of the aquifers that are depleted for agricultural activity and producing drinkable water. And then New York, another example that is subsiding mostly at the rate of 1 to 3 millimeter per year due to GIA effect and also compaction of the sediment along the coast. And we have two zones of rapid uplift at the center of the city, which is very surprising and took us a while to find out what's going on. It seems to be recharge of the aquifer. In a short period of time, they injected a large volume of the water under the ground, and it caused a rise of the land. So in these slides, almost 20% of the cities of the area of the cities are sinking. To just summarize the outcome of these 6 studies. So now we look at exposure of these 28 cities to land subsidence. So the bars show which part of the city area are exposed to what rate of land subsidence. So just to put in perspective, city of New York, almost 99% of the city is sinking at a rate below 0, and almost 15% of the city is sinking faster rate of the sea level rise, as you can see. And then Houston, Texas, quite a bit of the city is sinking, and large part of the city, almost 8% of the city experiences subsidence rate faster than 10 millimeter per year. So we look at the population exposed to land subsidence. Across these 28 cities, we found out that 34 million people are exposed to land subsidence. This is roughly 1/10 of the US population that is living in these 28 cities. And again, to put it in perspective, in the city of New York, 8.7 million people are exposed to land subsidence. And of that 8.7 million, 100,000 live on the coastal region of the New York. We would like to know how that land subsidence impacts the infrastructure. So we look at the risk that land subsidence causes to infrastructure to a risk matrix analysis. I do not present you the methodology, but I'm happy to discuss it at the end and point you to some of our publication that we established a framework to use land subsidence for investigating building damage risk for metro areas. So a few cities are shown here, color-coded to the risk of the land subsidence driven building damage. As you can see, majority of the cities experience very low risk, which is expected. We don't see building collapsing every day in these cities. So, but there are places, specifically in Austin, Texas, that in the perimeter of the city, we see areas of very high risk of building damage due to land subsidence. So to summarize that, for those 28 cities, we see 29,000 buildings located at where the risk of the building damage due to land subsidence is very high. And in New York alone, we have 299 buildings that are exposed to high risk of the building damage. And again, San Antonio among those cities has the largest number of buildings that are exposed to high and very high risk of the building damage due to differential land subsidence. Focusing on New York City, a densely populated metro with significant socioeconomic importance. So large part of the city, particularly over this box that includes one of the key airports, is subsiding at a rate that it's faster than a few millimeter. And that's where we have the highest risk of building damage as well. As you can see, some of the buildings that have risk of very high to very high are located within this area. And I just show you two of the airports in New York, LaGuardia and JFK, that their runways are impacted by land subsidence, differential land subsidence. And this is important because when runways are subsiding, it causes a different problem. One major issue, of course, is damage to the runway, increase the maintenance, but also the other issue is changing the drainage network. So runways remain flooded, inundated following, for example, rain and storm. That can cause problem for landing and taking off airplanes due to reduced friction coefficient. That in long run can cause issues if it's not taken care. So going forward, we talked about observation of the land subsidence. We talked about impact that it has on communities, infrastructures, but it's important to put forward a framework to combat land subsidence. You know, here we propose a framework to adapt and mitigate adapt to and mitigate the impact of land subsidence. So while we put together adaptation and mitigation, it's important to know land subsidence, as I mentioned, has two main drivers, natural and human-made. Natural drivers such as GIA impact the Earth as a whole. So there is very little we can do to stop them. So for dealing with them, the action must be adaptation. While when land subsidence is driven by human activities such as extraction of the fluid, the mitigation strategy might work better. So for that reason, we propose this framework that started with assessing the land subsidence. We need to collect measurements about the land subsidence, but also the impact that it has on infrastructures. Those has to be documented and provided to everybody to be used for decision making. And then once the assessment is done, we have to decide on the mitigation and adaptation strategy. One key mitigation strategy that I'd like to highlight is to reverse the impact of aquifer depletion of the aquifer is the managed aquifer recharge. Particularly, we are living in an era that wet seasons are becoming wetter and dry seasons becoming drier. So we can, build infrastructures to collect the water when we have too much of it and treat it and put it underground and save it for when we have less of the water. And through this process, we can mitigate some of that flooding that happens due to the excess runoff, but also reduce the land subsidence that happens due to compaction of the aquifers. And then it's important to engage with communities. So no adaptation strategy and mitigation strategy is successful if we do not get engaged with communities and co-produce knowledge and decisions and take into account their wisdom and educate them about the possible solution. And then once this is done, the whole process should be iterated. So there is no optimal solution at first. So we suggest that this process of assessment, action, engaging, impact, and monitoring has to be done in iteration to eventually reach an optimal solution that is cost effective, takes into account the interest of the local community, but also is effective in mitigating the risk and hazard. So as a result, the outlook is here, outlook of our research. This is something that we are hoping to also accomplish through this new initiative with the United Nations, the Global Lab for Environmental Intelligence. So we demonstrated ability to produce high resolution, high quality measurement of the land elevation change using spaceborne synthetic aperture radar. This technology is mature, can be applied to any place around the world. We can produce data at very low cost and make them available to everybody around the world to be used for decision making. What needs to be done is that once those maps are produced, to assess them, to interpret them, to create knowledge that educates stakeholders and decision makers to interpret this data, and based on that interpretation, decide with the right course of action, whether is mitigation or adaptation or doing nothing, because the impact that a hazard has is below the threshold that needs to be met to trigger an action. And for that, I conclude my presentation, and thank you very much for listening to this presentation.
Thank you so much. That was excellent. I wonder if you could go back into a little bit more detail first about how you examine building level land subsidence.
Right. So we measure the land elevation change or land subsidence using interferometric synthetic aperture radar. So this data has a resolution of few millimeters. So we can measure the change in elevation within a pixel size that is a few meters. So for Sentinel specific is about 3 meters by 12 meters resolution. So many building footprints actually are bigger than that in most cities that we discussed. So we have multiple observations at the building level. So, and we have access to other satellites that have resolution of 50 centimeters. So we can improve the resolution as it's needed using interferometric synthetic aperture radar technology.
I wonder if you could talk a little bit more about some of the potential causes and attribution of land subsidence. I mean, when I saw your map with the images of Houston, my first thought was, oil and gas initiatives. So I'm wondering if you could talk about how maybe some of the challenges in attribution, whether WAB-INSAR has been used in any kind of litigation or demonstrating causes.
So or significant advancement has been done on the monitoring side. So WAB-INSAR produces a measurement of the land subsidence at very high resolution accuracy. Attributing that to the driver is an ongoing research. So we need to create multi-objective models that can account for different physics, because the physics of the land subsidence, driver of land subsidence, whether it's tectonic or fluid extraction, is entirely different. So we need to create those kind of model, and then we need to collect measurements, data to inform those models, to be able to those are physics-based models, to be able to use them to distinguish contribution of the, for example, natural process from anthropogenic. However, we made significant advancements in using data-driven model, machine learning, but also statistical models to at least distinguish between different drivers based on the correlation that they have with different factors. So for example, what is the component of the contribution of the groundwater extraction versus droughts in observed land subsidence in those cities. But as I said, this is an ongoing research, and but to be able, again, back to that framework, to adapt and mitigate land subsidence, first step or second step after monitoring is to learn about the drivers. If we don't know what drives land subsidence, our adaptation and mitigation strategy will likely fail to result useful consequences.
Okay. Thank you so much for the presentation. It was so insightful.
Thank
and
you.
I look forward to reading your paper tomorrow. So yeah, we did this research and we realized that coastal cities are the front line of climate change adaptation. And whilst high-income countries are likely to implement institutional and infrastructural reforms, communities in low-income countries are urged to adopt behavioral change strategies to overcome climate change impacts. Now, you talked about models that we can use to maybe identify these changes and maybe provide solutions. How transferable are these models to communities in Global South?
So the physics of the drivers of land subsidence is universal. So the physics that govern, for example, compaction of the aquifers in Texas is the same as the one that does in Indonesia. However, the models needs parameters that has to be informed by the local hydrogeology, particularly for the groundwater. And same goes for tectonic and so on. So to summarize the answer, the models are universal, can be applied everywhere. However, local knowledge of the mechanics of the rocks and the hydrogeology is needed to inform those models to create a robust result.
I wonder if you could go maybe a little bit more detail into the framework that you showed, the last slide, and how you would use remote sensing data and this kind of information in municipal planning or zoning policies.
So can you repeat the last part of the question? How we use InSAR or remote sensing for zoning?
Yeah, how you would incorporate this kind of, how
Yes. So the proposal is that before expansion, before issuing permit for building, deploying similar technology to monitor the land elevation change, land subsidence measurement, and then use those land subsidence measurements in issuing the permits and requiring certain type of the building codes to be implemented. So, for example, area that is experiencing land subsidence due to compaction of the sediments, buildings cannot be tall, and if they are tall, the foundation has to reach the bedrock, for instance. So this is how we can use this measurement to inform zoning and planning and urban area development.
I'm thinking back to your previous presentation last year about how if you're looking to move to a new place or buy a home, the first thing you should do is check risk of land subsidence.
Yes.
And that really kind of stuck with me. I guess I'm wondering have you noticed, is there a change in that direction? Are people increasingly starting to think about this? What's your experience?
Oh, yes. Every week, once or twice, I get a phone call from major players, owner of a massive company that operates shopping mall across the America or other continents, that they want to build a new shopping mall or expand it. That's an example that if it's a good idea and if I can help them with my data set can tell them whether it's a good idea to build that massive infrastructure at a certain location. Or I get called from owner of the house that property is on the landslides or is on a slope, and if it's a sliding, what they should decide. So the awareness has increased significantly since last time we talked, and that's why we are thinking actually to create a service through this UN initiative that provide data, actionable data to everybody. So everybody can come to our website and look at the data that is already processed and is available. And there is data analytics available, with the help of AI and machine learning. Even ordinary user can use our data and make, create useful maps that can help them with their decision making.
Thank you. And Nikahan Kozawar says, thank you, Professor Shirzaei. Given that land subsidence is described as a silent earthquake, how might the interplay between gradual ground collapse and sudden seismic events in earthquake-prone regions affect the physical safety and psychological resilience of urban populations in vulnerable areas?
Yes, excellent. Oh, sorry, you're done or?
Yes.
Excellent question. So as I emphasized earlier, land subsidence alone, if it's only a player, it's unlikely to promote the building damage in a short period of time. There are places that we see tens of centimeter land subsidence. In those areas, you must see damaged infrastructures only due to land subsidence. But in many places that we studied, land subsidence is a gradual process. But land subsidence has this effect of amplifying the negative impact of other hazards. So, for example, if there is area that buildings are exposed to, for example, hurricanes and storms, just the pressure of the wind, stress due to the wind. If the building has been already exposed to differential land subsidence, meaning it was tilting to one direction, that wind can promote the failure of that building a lot easier compared to the case we didn't have the land subsidence. Same goes with the area prone to earthquake. If the building has been tilting, any kind of shaking can promote the failure and collapse of that building. So for that reason, in the seismogenic zones, any land subsidence is likely to promote and exacerbate damage due to the earthquake.
And you have another question that came in. Land subsidence is very important for early detection of infrastructure damage, I think as you were just talking about, including water and sewer pipes, and also to stop consequences, damage to infrastructure, sinkholes in streets, before becoming a catastrophe. And the accuracy of the images is really important to avoid confusion with surrounding buildings. Are the satellite images enough to measure changes on the roads inside cities? And which satellite image do you recommend used? Is this something that could be used using your software? And then there's a second question. Are there any APIs available that we could integrate your solution into other useful applications?
Again, very good question. So this type of the satellite, so free of charge data is Sentinel-1 at the moment, which is excellent data sets, the best that we had so far. And InSAR satellite is going to be launched soon, and in a couple of months, it will pass the initial stage and data will be available probably by end of 2025. And this data set can be used to monitor every and any infrastructure. And I want to emphasize that if you see a crack in the building foundation, it's too late. So already failure initiated. So the advantage of technology that I presented here is that it's very cheap, very inexpensive. We can monitor the entire city of New York, which is covered probably by 1 or 2 satellite frames in a short period of time. We're talking about a couple of days, and the cost of that is very minimal. So every city can employ or service and use our data set to monitor the city, and through the time, every 3 months, every 6 months, they can update this measurement, and based on that, they can create a priority list of infrastructure that has to be treated, has to be maintained. So think about that as an insurance or healthcare system or approach toward infrastructure. When age goes up, we have to go to doctor every couple of months to do the checkup and identify early warning for example, cancer. So you don't want to wait for a stage 4 cancer to start treatment. That would be expensive and likely treatment will be unsuccessful. Same for infrastructure. We can monitor infrastructure every 6 months, every couple of months, and identify precursory signal in our measurements that would tell you which infrastructure might be at the higher risk of damage. And through that, you prioritize the maintenance and investment. In this way, you don't have to have money to maintain everything at once. At the same time, you're likely to spend less for your maintenance. So this inexpensive technology can potentially save billions of dollars and save many, many lives in long run if it's implemented the way that I described.
Yeah, thank you very much, Manu. Excellent presentation, very informative.
Thank you.
This is not my area, but it's very exciting area. There's no doubt about that. Yeah, you mentioned the range of land subsidence at 4 millimeters, while the sea level rise is also 4 millimeters. So in total, basically, the effect is 8 millimeters. That's what I should understand.
Yes, the relative sea level rise that drives the flooding hazard for your location is 8 millimeters per year.
And the second question about what you were mentioning that the businesses, industries are maybe even people who are buying houses, they contact you. Do you know, because I see some of the insurance companies here, they do consider now these type of what they call the houses which are more exposed to these. You see when there is a flooding happens and that area is rather prone to flooding or not. So is there some sort of what should I say, move in the business arena to look into the insurance arena, that they look for the hotspots of this type of challenges, and then they may raise the insurance rates or whatever that is. Yeah.
Yes, that has been a trend. Actually, some of my students got very good job with a very good pay actually in insurance companies to help them produce this data to be used for adjusting the rate of the insurance. Yeah, it's a new trend and it will grow even faster. Very
sure, it will grow. Yeah, thank you very much. Thanks.
And we have another question that just came in from our colleague Sogol Jafar today. She says, can you tell us more about the Environmental Intelligence Lab? What are the next steps? How can we find out more and potentially get involved in these efforts?
Yes, so we will have an official launch for the center, and there will be website. But the center has 3 pillars. So the first pillar, creating environmental intelligence that is used by everybody through the expert community, like such as yourself, that would participate and collaborate with the center. The second part is educating public through educational materials, social media, videos, training material, etc., etc. But the third pillar, which is equally important but probably more impactful, is engaging with policymakers. So we are hoping that through this UN platform, we can engage with policymakers and educate them to use environmental intelligence for making better decisions that impact environment, but also people who live in that communities.
Yeah. On your point about education and engaging, are there any plans for any kind of citizen collected data as well?
Yes, definitely. That's one of the key components that we are thinking about, to include that and take the advantage of everybody's interest in collecting data that can be used for any purpose that has profits the community.
Would there be plans for any sort of real-time interventions if, for example, there was a detection of land subsidence, stopping activities? Is it?
Yes, that's one of our plan, to have to implement a sort of early warning system within the environmental intelligence. That is, the topic of early warning has been around for a while and is gaining a lot more momentum in recent years, thanks to earthquakes early warning and need for earthquake early warning, but landslide early warning, flood early warning, etc., etc. So we are hoping that we can leverage some of the existing expertise and create at least input, if we don't implement the early warning itself, but at least create data and input in semi-real time that can be used for early warning.
Yes. Sorry, Manu, I had to step out in the middle of your talk to go to another meeting and come back. Wonderful as always, and thank you again for all of your contributions. And we really look forward to make the lab a successful thing and very helpful to the member states and others. Let me ask you a question that I don't have an answer for. What is environmental intelligence? What does it mean?
Any information from environments that includes the natural environment, built environment, and everything in it, human, trees, plant, that can help to make a decision that has benefit to everybody. So this is how we want to define environmental intelligence. And still I'm working on a position paper. So we want to really coin the term of environmental intelligence to make it something that everybody feels the need. This is the data, you need it when you need it.
Yeah, and I should send you this funny cartoon that I use, and that's about the process of converting data into wisdom and intelligence, because data that must first be turned into information to others. So there is a process there into turning data into something that would be useful. And I think in the definition, we can bring all these elements, because one thing that people need to understand is that, yes, the fourth industrial revolution gives us a lot of data. We lost Manu. So it gives us a lot of, provides us with a lot of data. We need sometimes too many data points that can be confusing or can lead to misinformation and disinformation if they're not interpreted by the right people. So environmental intelligence not only requires satellites and remote sensing and data expert when it comes to extraction and processing, but also context, people who are expert in the matter to be studied and analyzed. And it's only then that we can provide something that is useful to the community. And I think we got to be careful, because sometimes we get too comfortable sitting in our offices and ivory towers and speak about what's happening, in the rest of the world. And yes, you can now even track the missiles that were launched, or last night, the sad incident of India attacking Pakistan. But you don't really understand what is going on, and we got to be careful about all those things. And I think this is very important for the scientists of the global north, to understand that most of the times we know less than the farmers who are on the ground. So the fact that we are seeing that groundwater is level is declining somewhere in India doesn't mean that this is new information. So that's something also, to understand. And I hope the lab that we are going to launch, and you'll be serving as the chief scientist of, can be beneficial and helpful and useful, not only in providing those early warnings and quick disaster response related information, but also in the scientific definitions that you just talked about. Your work is very, very interesting. And we are also discussing if we can add more on land subsidence to the upcoming UN water products and UNESCO also products. And I think it would be useful to warn about this. Still, this is something I think I want to ask another question from you. I talk more than you, maybe. Sorry.
Oh no, thank you. I'm listening, and I appreciate that. These are great. Thank you so much for sharing.
Yeah. One other thing is land subsidence is a gradual process. And if you are a decision maker in a city, if you're running a city and you're seeing the land subsiding, which is the result of course, farming, construction, and so on, how would you respond? Like, what is the best response strategy? And shall we also, on our side, shall we warn, create these warnings? Because we have also learned, I learned it recently in a conference in Germany that in some places actually were in the global south that people were not familiar with the process. They reacted too aggressively. They displaced people, and then they realized that things were not as bad as they thought. So,
Right.
What should we do?
Right, that's an excellent question, and I face that question often. That policymakers, mayors say, "Oh, this is a slow process. Do we need to care for it?" And my response always is that this is an opportunity. So, because many other hazards are not slow. So, land subsidence is slow, but it's steady. So it accumulates, and we have a firm knowledge that accumulation of land subsidence can cause irreversible damage to infrastructures and so on. So, but the slow nature of land subsidence gives us enough time to implement long-term policies to combat that. So this I always see a positive things about land subsidence. But again, we have to avoid hasty decisions such as the one that you mentioned, displacing the community. That probably would not have been necessary. And our assessment, for example, for a city like New York suggests that land subsidence that we observe today can cause damage to building in 30 years if it's not mitigated or adapted to. 30 years is a plenty of time to create policy and allocate resources gradually over the time. So this requires changing the perspective because, as you probably know better than me, most of the policymakers are in office for a short period of time. And they focus on short-term decision to justify why they were elected and possibly why they should be re-elected. So this is a problem we have. So land subsidence requires policy that spans over several administrations. And for that reason, I'm not sure democracy is a good thing to have.
Okay, that's very extreme. This is not a UN scientist talking. No, it's a Virginia Tech expert.
No, I'm kidding. So
we have
it just
disclaimers.
So we really need to change our perspective. We cannot always rely on short-term solutions, because if you focus on short-term solution, which goes from election cycle to election cycle, subsidence always falls off the attention, and only the last person end of that cycle, the third or fourth president, has to deal with all the consequences. Bridges collapse and pipelines break and buildings experience failure and so on, and then we have blame everything on that one person. So that probably is not constructive approach.
Yeah, but I mean, that's the reality of the political world, and it has been forever.
Yes.
It's not limited to land subsidence. Just quickly, because we're out of time, have you seen any interest from the insurance companies in your work?
Many. It's picking up so much that I have almost a call every week. Sometimes 2 calls a week from insurance companies, not only in USA. Yesterday, I was on Monday, I was on a call with people in Chile and Peru, a company that operates across the 2 countries. And then European companies reach out, Germany specifically, that they want to use this technology for, creating a better plan for insurance.
To charge more.
Yeah.
No.
I don't think anybody would reduce the price, but yes, I think they want to charge more.
Thank you. And so hopefully you'll be rich soon and you start donating money to us. So back to Miriam. Thank you.
Thank you so much for another fabulous science talk. We're really looking forward to hearing more about the Global Lab on Environmental Intelligence. Thank you, Professor Shirzaei, new inaugural Chief Scientist, and we look forward to having you back again.
Yes, thank you very much. It was a pleasure. Thanks to everybody for all the great Q&A and opportunities to speak to you. Have a great day.
Thank you.
Bye.